say some things more to complete the problem that we took yesterday, and just round it up and tell you a few more remarks. So this should be very simple. So Professor Romito talked about invariant measures, and he took the periodic boundary conditions. So worked on the torus. We can also take G to be with periodic boundary conditions. That actually simplifies certain estimates and so on, right? Yeah. Can you hear me? Yeah. It's on. Oh, no. Maybe I was mumbling. Mathematicians do that often. G can even be the torus. G can even be taken to be the appear.
Q. Can I ask the same question as the question was yesterday?
Yeah. Okay. Oh, larger. Sure. Okay. Larger and louder. Okay. All right. So, in the last class, we proved exponential stability, and in that setup, you cannot really conclude that there would exist an invariant measure and so on and so forth. You cannot talk about ergodicity because the sigma was dependent on t, right? If you make something depend on t, then you are not guaranteed that the Markov process would be time homogeneous. And therefore, it would be an evolution semigroup, right? And that's not good for us. Therefore, we'll make it today much simpler. We can take sigma to be just made up of sigma ij's, okay? So it doesn't depend on t, let's say. And summation of sigma j squared is less than or equal to some L finite, right? And we said that L should also be small enough depending on what the viscosity is. Are you able to see this? Okay, I'll write it even bigger.
The problem is how hard you press.
Yeah. All right, I'll press it.
Some chalks tend to be darker.
I see. Yeah, these are a bit lighter. Okay. All right, I'll do. So then we all know this Px of Pd, right? That's the probability that our u of t comma x belongs to the Borel set B, correct? So what is the underlying semigroup? S sub t. So this is just by way of recalling. And this would be the expected value of phi of u of t x, right? Now this corresponds to the solution of the stochastic Navier-Stokes equation that we considered in 2 dimensions. Today we can even have a simpler boundary and so on. And sigma doesn't depend on t. Therefore, it's a simpler case. And S sub t, is it, S sub t is Feller. Why? Because you take st phi of x, right? Well, I have written here what it is. And supposing xn's converge to x, for if x sub n converges to x, these are the initial positions, yeah? Then u of tx, we proved almost surely, right? As n goes to infinity, even exponentially fast. And to prove Feller, what do you take? You take phi to be in as a continuous bounded function on edge, right? Therefore, That's quite easy. All I'm using is bounded convergence theorem. Yeah.
I'm not sure if I remember correctly, but as far as I remember, it is a result that to prove that the Ferret property is enough to prove for Lifschitz functions.
Okay.
Then sort of simplified in some cases.
Yeah, I'm not even going to invoke Strong-Feller today.
No, yeah. Just Feller. I think.
Yeah, that's what I mean. I have Feller, and I will now show quickly that there exists a ergodic measure, and that it's going to be unique. Support is going to be in V, that it has second moments, and so on and so forth. All right? So first of all, we have to go for the existence of an invariant measure, right? And the way that I told you about, I didn't prove it. It is the result by Krylov and Bogolyubov, Krylov, whichever way you call it. Okay. So let's first of all say, write down a theorem. So the theorem is going to be there exists a unique invariant measure. And the proof. So first of all, you all remember the energy equality, right? This is in 2D, therefore it's an equality, as was explained yesterday, right? So let's write down u of tx, okay, squared. Let me write everything that I like here. 2 nu integral 0 to t norm of u of tx squared ds equals what? The inertial term goes away, right? As was explained. That's the nicety about the energy. That means the mix-up of the in the fluid, the dynamics of the fluid is such that energy is not increased or decreased by the nonlinear term, right? It drops out. And what should I put on the right-hand side? Anybody remember? U was 0, right? At 0 it is at x, right? I can put that. And then our noise. You can even have some more external terms. I removed all of those because it doesn't add to anything. And then there is a martingale. And then what is the extra term due to 2 and 2 cancel out. The 1/2 and 2 cancels out. So you have an integral 0 to t. But then the summation over j of sigma j squared, that's independent of time. Therefore, I need not have written it as an integral, right? I could have just stated it as this times t. Okay, so let me do that also. Okay. Therefore, let's take expectation. When you take, okay, how do I know that it is a martingale? It's not a given, right? A lot of people write as though it's a martingale. It's actually a local martingale. You have to use stopping time arguments and then say that it's in the limit, right? It's actually, everything is 0. The expectation is 0, right? So, let's take expected value of u of tx. So I'm making here a very simple calculation, 0 to t. ds. Let me say that it is less than or equal. So I take an expectation, this is 0, and I get a x squared. And then what else? Sigma j squared term is still there. I had to just write it You can see that these things can be somewhat generalized and so on and so forth, but as I told you, I'll just give the simplest of statements. Now divide by t everywhere, all right? Shall we do it in the same one? It's all equal, huh? I didn't do anything to make it larger, right? Let's say. And then divide by t, and then when you divide, this is gone, and you get division by t, right? So it's all anyway less than or equal to a constant. Even if you had started with a random time, this would have been the case. Therefore, the thing that we get to observe is this quantity is bounded by a constant for all times. Thus, 1 over t integral 0 to t agree? For all t. And using this, you can prove the tightness of the measures that we wrote in the Krylov-Bogoliubov argument, right? So, the next thing that I'm going to write is, since this is true for all t, I can say that limit as n goes to infinity, supremum over t How do I get this? Just Chebyshev inequality. All right. This would tell us that therefore, you'll understand, because this can be bounded by 1 over n squared times the expectation, right? See, this quantity is less than or equal to 1 over n squared times and then the integral is there, but we have proved that everything is less than or equal to c. So it is c divided by n squared. As n goes to infinity, everything is 0. All right. Use this. Using this, one obtains. So there is not much mass beyond the ball of size n in V. Right. Therefore, eta t super x, if you define a measure like this, which is, let's say, I think that's how I have called it. So define for any set gamma, define this measure to be. We have seen this before, but then we didn't spend much time since I was hurrying on to prove other things. Tx, that's what the x is there for. Tx of what? SB. Oh, gamma. So this is the time average of the measures, right? And we'll give it a name here. This, let's say 1. Using 1, use 1 to show that, to say that. Eta Tx, this measure, t greater than or equal to 0, right, is tight. Tx, oh, that means you are starting at little x, and then at time s, your process is in the set gamma. So it's the transition probability. Is tight. In the space of probability measures on H, equipped, so whenever I talk about a space of probability measures, it's equipped with the weak convergence topology, right? Okay. Therefore, we know that tightness is another name for relative compactness. Who proved it? Prokhorov, right? You will all see it in the probability theory course later on when you see convergence in distribution. Therefore, there exists a subsequence, right? There exists a sequence rather. Tn increasing to infinity such that eta Tn x indexed by n is, converges. I'll write it neatly. Converges weakly. I should put a mu super x, but then it is going to be independent of little x. Okay? But then we don't need, yeah.
Where do you use the fact that it's 2D?
Where do I use that it is 2D? Good question. Well, in saying that the set that I'm considering is compact, right? Yeah. The ball, the V ball in N, of radius N, right, in H, right? Because I took a specific domain, namely I'm working with Q.
Today's calculation,
Yeah.
yesterday of course you had this exponential.
Correct, yeah.
It's 2D, you know.
Correct, that's 2D.
But this one, so far you haven't used the fact that it's 2D.
That's right. This is just the Krylov-Bogolubov argument. It holds, yeah, in general. Huh?
Just the energy estimate and then you...
Right. It would have been an energy inequality and so on, right? Right? That's right. That's right.
The estimate you could have also if you have a Martin solution.
Exactly.
So all solutions satisfy this type.
Right. If you have a unique, if you have a solution,
So that is why for
yeah, you can do it. Yeah.
Which is in the case when you have no sort of invariant measure, in the case when you don't have invariant measure. Because you are right, the estimates are true. The problem is that what is in the real Markov process has not been used here. Used in background.
Yeah. To say that it is Feller and so on, which I'm going to use right now, right? Yeah. Next step. Yeah. By Feller property, or the semigroup, ST phi is continuous. We just now proved that it is Feller, right? So, what is weak convergence? I can even take my function to be, I can written it all in terms of carefully chosen notation here. Eta T and x dy. And if I take the limit, okay, first of all, if I just start with mu, let's say mu dy, that is the limit as n goes to infinity, so that I have things continuing. So whenever I have an integral, it is integral with respect to on h. And this would be the same thing. Eta Tn x dy. Why does this happen? Because this is an equivalent formulation for weak convergence, right? So you would have all read about convergence in distribution by saying, oh, it converges, mu or eta sub Tn of gamma converges to mu of gamma, provided the boundary of gamma is not charged by eta. That is, eta of the boundary of gamma is 0. Things like that, right? Here gamma is, I could have even replaced gamma by some b. Okay, because you may think it's the boundary of a domain or something. Okay, that's all I need to do. You all understand? But then that's a very difficult notion. You don't always necessarily have to start with the definition. Therefore, you say that, okay, eta sub Tn converges to mu weakly, provided this equality holds for all integrands which are bounded continuous. You know that, right? You can also take that as a definition, then you don't have to prove it. This is the more useful of the definitions. So how do I know ST phi is continuous? Because we have proved that it is Feller. Therefore, if phi is continuous bounded, ST phi is continuous bounded, right? So I always CB of H. So far, okay? You're all following me, right? Kind of. Even if you get some percentage of it and then read up, it would help. Okay. Now, this is just a measure that is described here explicitly. Therefore, you have to, if you want to write it in a more nasty way, it will become 1 over Tn integral 0 to Tn, and then what? There will be a S sub S, because you got to put this S sub S and then average it, right? XD, because I had to, when I'm going backward, I have to finally go to the original starting point, ds. Right? Is that clear? Or did I go too fast? We have done this before. So the action of eta Tn is just to take the time average, divide by the time, and then you put then work with this measure. So the ds measure is there. This measure is absorbed by putting S sub S here, because that's also an integral actually, right? Yeah, whenever you put the semigroup here, it means an expectation. That means it's an integral. Okay. Therefore, all in all, this becomes limit Sn goes to infinity of, I can write this as S of S plus T because of the semigroup property. Therefore, now there is no integral here, right? Maybe that was bothering you all. There is no integral. That's it. Sorry. So, you don't understand? Okay, let's work out, right? You have st phi of y, and then forget about this. This is the easy part, right? And then I also need an integral over h, right? And I have to put px, okay, of, from here I'm integrating with a parameter called s, right? And then what do I have here? dz, let's say, right? dy. Correct, yeah, because it's y, so dy, and then there is a ds, all right? So this is, what is this saying? That means you are going s more units, right? So you started with x, and you are at y. Now from y, starting at y, you got to go t more units. So the net time spent is t plus s. So you can write this inner integral as 1 over Tn, integral 0 to Tn, S of s, right? That's the what is it? The Chapman-Kolmogorov equation. That's all it is. Yeah. And then you have a ds. Okay. So you all understand? It's quite easy, unless you are writing on the board. And this will become 0 to Tn. So this is exactly the proof of this Krylov-Bogoliubov argument. Right? And this can be written as limit as n goes to infinity of 1 over Tn. You can make a change of variable here and make it as t to t plus t. Easy? And then this is the same as limit as n goes to infinity 1 over Tn. Write what you want. You are supposed to go from t to t plus n, t plus tn, but you went only up to tn. So say, okay, I'm going to go from tn to t plus tn, or the same thing. And then you are going to say, oops, I went from 0 onward, but I'm supposed to go only from t, therefore subtract the 0 to t. So the same integrand is taken, right? Tn is going to infinity, and these guys are all bounded. The width of the interval is only t, therefore it all goes to 0. These two parts go to 0. Is that clear? There is a Tn, right? So if you are only integrating from over an integral of width t, and the stuff inside is bounded, then it is just a constant times t, but then it is divided by Tn, and Tn is going to infinity. Therefore, the last two terms do not matter, so we only get the first term. S or phi of x ds. And that's precisely the integral of phi with respect to this eta Tn, right? What did I say? Yeah, phi d eta Tn x. Right? But then phi is also continuous bounded. Therefore, this is going to be, we know that eta Tn converges weakly to mu. Therefore, you get it to be integral of phi d mu. So what have we proved? We proved that if you start with mu, then after time t, we have this integral. So this integral is equal to this. Isn't that the definition of invariance of mu? Right? So this is something I didn't prove, so I thought I'll prove it today. It's a very important argument. Sometimes it's a simple argument which is verifiable and becomes ubiquitous, right? It applies in so many cases, so many scenarios. Then it becomes very important. Questions? So this is just about existence of an invariant. Now uniqueness. Okay. Uniqueness of invariant measures. Okay, suppose there are two invariant measures, mu1 and mu2. We need to show what? We have to show that, show that integral of phi d mu1 equals integral of phi d mu2. Correct? If mu1 and mu2 are both invariant measures. So, assume that mu1 comma mu2 are invariant. So define some time capital, fix some capital T, and then eta Tx is there, right? Okay, so what is eta Tx? Precisely as in here. Pardon? Which? D mu. If you put the mu here, it comes out to be the mu here. So we got to show this for all phi bounded continuous in H, defined on H. Now we are going to use the fact that mu1 and mu2 are both invariant measures in writing the following. Let's consider the difference between the two sides, right? So I have to be Just give me 1 second. Well, so consider integral, absolute value of the integral of phi d mu 1 d mu 2. Absolute value. What can I put here? I can integrate with respect to eta t, right? Eta t x, eta t y, and so on. So I can put here a phi, fix any t, okay? Eta t x, mu 1 dx. Okay. That is exactly equal to, they are all equal to each other. And I'm going to write a similar thing for the next part. And we'll just make it as a y. I think I have 2 integrals, so I need 2 integrals here. Okay. D eta y of z or eta y of dz, whichever way you write, and then mu 2 dy. Why is this true? Because we can assume that mu 1 and mu 2 are invariant, right? Let me explain to you why this is so. So if you take this measure, for instance, what is this measure actually? It is 1 over t integral 0 to t. I'm just explaining to you what this measure is, okay? Acting on a set, B or something like that. So this would be pt, and it starts with x, right? Oh, p sub x of t. And if you had to go to some b, that's what that is. And then your x's are like, correct. But then what is this integral? This is okay. Now, okay. So if you call this this measure as some, give it some name, nu or something, right? Nu 1 of b or something. This is what you have. But then mu 1 is invariant. Therefore, what is this inner part? Irrespective of what s is, the distribution is stationary. Therefore, if you start with mu 1, then this is the distribution at time s. So this is also the boxed thing is going to be mu 1 of b. Say that again.
B is a DJ.
B, where?
Probability of x is
P sub x.
of t of x is dz.
Oh, I see, dz, yeah? Yeah, that dz comes in here. I made it integrated over the z and made it as b. If z lies in b, then it would become like this. Okay. Good point. I said that I'm going to write exactly that, but I don't really like differentials. That's why. Even in calculus, I don't like differentials. I think it's make-believe. And then there is mu 1 of b, and then there is ds, and then 1 over t integral 0 to t. This doesn't depend on s, therefore it is just mu 1. So the measures are the same, right? So this measure is the same as the measure mu 1. Got it? Easy. Everything is just from the Markov property, and yeah, right, the way we write, that's right. Same way, this measure is going to be exactly equal to d mu 2 when you write it in the differential form, okay. So I'm going to erase this. You can easily reproduce if you didn't write it down. And let me just, everything is something. I'll write down, I have an optimal way, I thought, but then So this part I'm just going to write it as expectation of phi of u of x of tx, or however we have been writing. d mu1, isn't that what it is? The action of eta t on phi is going to be 1 over t integral 0 to t of this expectation. I'm giving you another way to write it so that you get used to these. Which is why I look at this, it's nothing new actually. But then, let's do the same thing here. Let me write it as u of ty. So the expectation stops here. You understand? And then I get to write the dt d mu2 in absolute value. No big deal at all. It's all very simple. When you just sit down and then write it down, you'll be amazed as to how simple these are. So here, and now I have a question for you all. Will you be upset if I put another integral here over h and then simply say, so this mu1 is with respect to x, okay? This mu2 is with respect to y. If I here introduce another d mu2 dy, let's say. I don't know which way you all like. If I put in a mu2 dy, there is nothing which depends on y. Therefore, integral over the whole space with respect to mu2 is 1 because it's a probability measure. Likewise, here also I can slap another h, integral over h, and then put a d mu1 or mu1 dx. Because there is nothing here that depends on x. You understand? So that's very easy to do. The reason we do it is then the measures are the same. dt, mu, d mu1, d mu2, right? Whether you write it this way or this way, it's all the same. Therefore, I'll write it in that way. So what am I doing here? Let me not clutter this. I'll write it as a separate step. I just wanted to show you that I'm not doing anything that shouldn't be done. U of tx minus phi of u of ty dt d mu1 of x d mu2 of y. Do you all see the mu2 of y? Okay. And then you can end the absolute value. Then the absolute value can be brought inside, and if I am willing to put an inequality, shall we do that also? So that I don't have too many steps. So I put an absolute value all the way inside. So what are the things here? dt d mu1 of x, d mu2 of y. Okay, now we are in the business of showing uniqueness. You should always go back and realize what you want to do. That this has to be equal to 0, right? Okay, why is this now 0? As t goes to infinity, what happens? As t goes to infinity, the capital T is the same, right? Let me see. By stability result, phi of ux of t minus phi of uy of t, this inner thing goes to 0, right? And therefore, what can you say about the average? Cicero mean, right? That also goes to 0. Therefore, everything goes to 0 as t goes to infinity. What did I use here? The stability result, so that phi is continuous, and u of tx minus u of ty can be made exponentially small, right? And then simply now take capital T to go to infinity, you'll get that it goes to 0. That's all. Okay, so what have we proved? The proof. So
There you use exponential.
right, that's right.
There you use exponential.
Oh, just you can right. You can bound it. I just want it to go to 0. Right.
Yeah. So it appears to me. So far, let's say you have an invariant measure.
Yeah.
Then you have a Markov process.
Right. I showed that it is Feller.
That it has a unique invariant measure.
That's right. That's right. Well, I used the fact that it has stability, right? The result that we proved yesterday was used here. Huh? Yeah. That's right. That's right. More than what we require. Yeah. Okay. That's right. We need some stability.
Mod u to x minus u to y converges to 0.
Right. Right. Well. Yeah. Phi is continuous. Right.
Yeah, if it is Lifschitz, yes.
Yeah, if it is Lifschitz, it is easy, right?
Right.
And yeah, prove it for Lifschitz and then take the limit. Yeah. So it's I thought it all follows from just dominated convergence theorem and exponential stability. That's right. Okay, that's what I thought. And correct, the modulus. That's right. That's right.
The difference go to 0. It don't individually doesn't go to the point.
Right. You're right. Yeah. So go to Lifschitz continuous functions, and then pass to the limit. Yeah. That's.
They can use sigma not as a function of time, right?
That's right. That's right.
What will go wrong?
What will go wrong with all this? It will become an inhomogeneous process. If your coefficients depend on time as well, then I'm afraid. Huh?
You can prove the time tensor.
Correct. Yeah, but there is no semigroup.
That's the
Problem. Yeah.
Here the question.
Huh? Oh, he was asking me why can't sigma depend on time?
So Feller properties are.
Yeah. You won't have the semigroup. Yeah, you won't have the Markov property.
In this way, but you have
Right. You had to do it in the evolution semigroups is what you may get.
You can change your state space in the Markov.
That's right. You can join the little t as well as the state space. Yeah. Then you can do something. Yeah. So you got to redefine the state space and so on. Right. Yeah. Correct. Yeah. I agree.
More variable.
That's right. More variables. Yeah.
Right.
Now. Any questions? That's a good point. Yeah. Take phi to be. I thought I had a simpler argument. I had to look it up. But then simply do the take the phi to be Lifschitz continuous and then pass to the limit. Okay. Next one, theorem. So what have we proved so far? Let's just take. Let's go slower, which is what we are doing, and we have proved that mu is invariant and it's unique. Now we want to claim the next theorem is mu is unique. Mu is ergodic. Let me ask you before this, let me not keep on proving. If I show that it is ergodic, is it the unique ergodic measure? It is unique, right? Because you don't have any other invariant measure to talk about. Correct. Okay. But I'm just interested in, this is what we were wanting to do, namely that it is ergodic and so on. All right. So what is the way to prove? Suppose not. So let's prove it by contradiction. That means there exists an A, Borel set, such that probability of A, such that ST indicator A is indicator A, almost surely, and that means it's an invariant set. Remember, to show that it is ergodic, one way to do is invariant sets have measure 0 or 1. That was our definition actually, right, of an ergodic measure. So this is a fancy way of saying what? Can you write it in terms of probabilities and so on? What is ST indicator A? If I put an X, let's say, I'll help you out here. Mu almost all X. Can you tell me what the left-hand side is precisely with the probability measure? That means you are starting at little x, yeah? And in time t, your process comes to A. Right? So it is just another way of saying Px, Px of t A equals 1. This side, it is going to be 1 if x is in A, and 0 if x is in A complement. Of course, I just left aside the mu almost sure x and so on. This should hold for almost all x as measured by mu, right? Very good. The idea is now, if this mu of A is between 0 and 1, you relativize the mu to the set A, and that new measure is not equal to the mu measure. And it will also happen to be an invariant measure, contradicting what we proved, namely that there exists a unique invariant measure. That's all there is to it. So define. So what do I mean by relativizing mu to A? Define another measure. Oh, do it for some B or something, right? Mu of A intersection. So this is like taking the conditional probability. I can divide by mu of A since it is here, right? And it is not going to be, nu is not going to be equal to mu. Okay? Because nu of A would be mu of A divided by mu of A, which is 1. Whereas mu of A is 0 to 1. So this nu is really a new measure, not the old one. Now how do we show that it is invariant? So consider integral of Px, okay, of T some set C, let's say, nu dx. That is, I'm looking at the probability distribution at time t, right, over H. But nu only lives in A. Therefore, I can always say it is just integral over A. And then what else? Should I divide by mu of A? Because it says I get to divide by mu of A. So I'm worried about how to write nu back in terms of mu, right? And then what do I get here? Px of t C. Instead of nu, now I can put, since I have put integral over A, I can just put mu dx, right? Are you all in agreement with this? Okay. And now let's write it down as sum of two terms. So this is the same as, so this is a basic theorem. So here, this is actually a more general theorem, not just for this setup. A intersection C mu dx. I can write everything here. Write like this. So the first term what is it less than or equal to? It is less than or equal to Px of TA. Why? Because of monotonicity of measures, right? Which is going to be 0 if x is an A complement. Why is that? This is easy, right? You all know that this is a measure of A intersection C. It is going to be less than or equal to measure of A. Why is it 0? If x is an A complement, you have to see here, right? Px of TA, if it is an A complement, it's 0. Okay. I don't have to even do this. This is also 0, right? If x is in A, same thing. Mu almost surely everything, but that's fine. I'm just leaving aside a 0 set. Therefore, this is gone because I'm only integrating over A. So if my x is all the time in A, this becomes 0. Whereas here, I can extend the integral not just to A, I can also take it to be in A complement because P of T A intersection C, this integrand is going to be anyway 0. If it is going to be 0, you can integrate over the whole H, right? Therefore, integral over A, integral over H rather. So what happened is this part went away, and here I'm just putting a 0. It's a 0 on A complement. Therefore, I can always add it, right? Okay. So what is this? So when I said mu is ergodic, I mean this unique invariant measure mu. Therefore, I'm starting from anywhere, right? And then I had to be in A intersection C by time t. Since mu is invariant, this integral is exactly mu of A intersection C. You all agree? Since mu is invariant. Okay, that's it. Therefore, what is that measure called? It is nu of C, right? Another name for this measure is nu of C. So we have proved that the left-hand side is equal to this ultimate right-hand side, which means nu is invariant, contradicts the hypothesis. Because we said let mu be, mu is, you got to remember, huh? We know that mu is unique invariant. Correct? Therefore, our supposition is incorrect. Do you all see what the contradiction was? So we got that this law of the process, right? The measure of the set C at time t is equal to measure of the set initially, if you started with nu, right? With the new with the initial law being nu, which means nu is an invariant measure. It is not equal to mu, but mu is the unique invariant measure. Therefore, a contradiction ensues. Therefore, this cannot happen. Therefore, mu of A is either 0 or 1, which means mu is ergodic. I don't have to write these, right? I said twice. And this is a general theorem. Namely, here I didn't make use of anything about 2D Navier-Stokes in this theorem. I should have stated this and proved it maybe long time ago. But there was no time. Okay, so any questions? Nothing? Okay, so you can read more theorems and finer results. My job here was to give you the basic results and some idea about how to prove things. So I'll give you a list of some of the references, okay? In the next 5 minutes, and then I'll tell you something else. So before I erased, that's okay. You had to also note that this invariant measure has support in V. Why? Because remember the integral of norm U mu dx, right? Or however you can, no, I'm writing something incorrect. We made use of this, right? For all G. So which would show that the same bound holds for the limit measure, right? When expectation is taken with respect to the stationary measure, mu. And therefore, this quantity is finite almost surely. And therefore, the support of the invariant measure is in the set, in the space, V, which is dense in H. And okay, ergodic theory. I told you that it started with Hamiltonian systems, for instance, right, in those dynamics, and then also in stationary stochastic processes. So the first paper, important paper, appeared in 1932, von Neumann. Should I put a lowercase? Huh? Okay. So von Neumann's paper appeared in 1932. That's deemed, that's the mean ergodic theorem. Okay. That means it is in L2. In the L2 sense, nothing mean about it. And then 1932, there is also the result of Birkhoff. That's the ergodic theorem, point-wise ergodic theorem. These are all classical results. And then there are so many nice books on ergodic theory. For instance, when I was a student, I just like that happened to land on Halmos's book on ergodic theory. I forget what the title is. So I read it. He was talking about mixing and strong mixing, weak mixing, and then he was explaining it by mixing some alcohol and so on. Okay. You know Halmos, right? He has a way of writing. Then there are also books by, I was enchanted by it and then went to this book by Walters. This was all when I was in Chennai as a student. There were very few books, and these books, Walters looked very bright and nice, and I took it, and it was a fantastic book. And also Peterson. Okay, Carl Peterson, how does he, maybe he puts it like this, Carl Peterson. The book's titles are on like ergodic theory or introduction to ergodic theory. So these are all on the basics, yeah. the whole theory, so to say. But for stochastic PDEs or in stochastics, pardon? Yes, yes, yes. Hopf. 1952, huh? Oh, that's the book in German language. Right, right, right. So it's a book, I think, not translated in English. But then his paper, well, there were. So you can look at it. So in probability and stochastic analysis, the first book to seriously take this, to my opinion, is Hasminski. A book by Hasminski. Stability and what else? I forget the title of the book. It's available, huh? Right, something like that. Stability of stochastic differential equations. Excellent book, and it got reprinted, I think, with an additional author, right? In Springer. So then there was this book by. Well, there are several things that I may have to omit. If you all as students want to read something wherein the complete proof is given for the mean ergodic theorem for solutions of stochastic differential equations, go to the TAF for lecture notes by Varadan. At the end of the book, he proves the L2 ergodic theorem for solution of a one-dimensional SDE. Okay, on seeing that, we later showed such results for non-Markovian solutions of SDEs. So that's the mean ergodic theorem. You can also find it nicely described in the book by Skorokhod, wherein explicit expression of the invariant measure can be seen, just like what Professor Romito was telling us yesterday, right? Gibbs measures. Okay, so there are these, another book that's of more relevance would be Daprato and Zubčík. I think I spelled it right. And it is called ergodicity for infinite dimensional systems. Stochastic systems, maybe. I'll just write systems. So these are the books. So you may ask, what are the favorite papers, right? I'll just tell you papers wherein a remarkable idea is put forth, because there are too many. Of course, you can look at the references in here, and that will give you a plethora of papers, all right? So I'm not going to write down a whole lot. I will only say what I think is a bright, brilliant idea. I may omit a few, okay? So, there is also a small book by Cookson called some statistical hydrodynamics and something, okay? So this book is put out by the European mathematical community or something like that. So this Cookson and Shirikian put out a different approach, namely by coupling, right? Of course, when you consider an x and a y like we did for stability, anyway, a probabilist would say, oh, there is a coupling going on. I've been told that several times. Right? So Cookson's approach is different. We didn't even touch on it. There is a paper by, beautiful idea by Heirer and Mattingly. That appeared in 2006 in Annals of Math, where they extend this concept of Strongfellow, right? So that's a good paper to read. And Pardon? Correct, yeah, possibly degenerate, correct, yeah. And I'm sure there are many more. I should have made a list or something. Maybe I'll put at the end a reference list. Okay, this is what comes to mind. And oh, there is also a famous paper by Albuverio and Cruzeiro called flows for Euler and Navier-Stokes equations, right? So there is also a nice, wherein they talk about the Gibbs measures, right? Serge Albuverio, Cruzeiro in our department is called ABC because her initials are A and B. And this appeared in Communications in Math Physics, I think. 1990. And also there is another paper that I'll put here, Flandoli and Maslovsky. Again, Communications in Math Physics, I think. Maybe some of you know these things better. If the references are wrong, tell me. But then it doesn't matter. You can just Google these days and get anything. Okay, now I have 20 more minutes. And what I'm going to do is, yesterday it said that there was a deterministic system apart from Navier-Stokes, okay? And that it's approximately controllable under some conditions. So that wasn't proved. So I'll just make this as an addendum because Professor Sridharan was interested in it, intrigued by it, right? So we will see what it is. Any further thoughts on this? Have you all? So this is a completely different approach. And so is this. These two are different from this. And these two, I think they explain Professor Flandoli's result in Daprato and Zapchik. And there is also a recent book by Gavaretsky and Mandrekar. Mandrekar is from India. He's from Goa, actually. And they wrote a book on stochastic PDEs, wherein chapters 5 and 6 deal with invariant measures. And the way they do it is by the concept by Lyapunov functions. Okay? So there is something called ultimate boundedness, and then use Lyapunov functions. There is a way to show invariant measures. That's a paper that goes back to Ichikawa. I don't know offhand where it appeared, some Japanese journal maybe, I don't know. So if you type in Ichikawa or look in Gavaretsky and Mandrekar, the book by them. So that's a completely different approach, right? There are, of course, connections to each, maybe. Somebody can analyze what the connections are. And that's another way to look at the problem. So they consider always mild solutions, right? Ichikawa. Okay, now I will lose time if I talk too much about these. I'll go to this controllability issue. So, what was our equation? I called it as, if you recall, derivative of x of t with respect to t equals ax of t plus fx of t. Is that it? Plus sigma. I wrote theta of t on h. And then x of 0 equal something, z or something. Theta takes values, and so this is something we made use of yesterday in proving irreducibility. Theta belongs to L2, fixed on T. So that's a control term. And I said that this is approximately controllable, right? Where f has the nonlinearity, namely it's just a Lifschitz nonlinearity. Okay. This has a unique mild solution and all that. A generates a strongly continuous semigroup, and so on and so forth. Okay. So, what was our notation? Okay. I'm putting x of t, z naught, u, and stuff like that. Okay. So the condition is that that we put is that range of sigma, range, is dense in H. Okay. Then the claim is then what is it? Yeah, we have approximate controllability. Okay.
So the sigma is a map from H to H?
Yeah. Sigma maps from H to yeah, sigma acts on H to H, correct. And F is also from H to H, and it's a globally Lifschitz. I mean, it's a Lifschitz. Lifschitz, yeah. And proof.
F is essential that it's globally Lifschitz.
I'll be using it because I want to find the simplest proof. Yeah. One can think of something else. We will go through the proof and it will become obvious. I'm just geared towards ground volume. Okay. Let me not think too much. Let Z0, Z1 be members of H. Those are going to be the starting points. Okay. And these are all, take any of these. T is also given, epsilon, anything given, and so on. For any Z0, Z1 member of the domain of A, okay, define alpha Z0, Z1 of T to be simply T minus T divided by T times Z0 plus T over T Z1. So I'm able to go, right, when you put time T to be 0, then it is, I'm going from Z0 and then it ends at Z1, right? Okay. Now define. I'll write it and then tell you what it is. Derivative of alpha with respect to t minus a alpha minus. So what did I do? I just plugged it in here and then took these two terms to the other side, and instead of, I won't get a sigma theta because I don't know whether this simple-minded process solves anything. Therefore, whatever I get, I call it as beta 0. Are you all with me so far? Yeah? It's okay? So there is no stochastics in this. So if you don't like stochastic analysis, it's great for you. So let's call this as 1. Now, choose Z0, Z1, member of domain of A, and sigma and theta, let's call it, member of C of 0t H such that 1 Z0 minus Z0 is less than epsilon. Same thing for Z1 minus Z1 less than epsilon. And beta Z0 Z1 that we have, right, minus sigma theta of t to be less than epsilon. So the reason I'm able to do this is because of the denseness of the range of sigma in H. Now consider absolute value of x of t z0. I have chosen my, let me just write down, there is nothing at all to this. It is less than or equal to this quantity minus x of t. I'll start it with z0 and theta plus x of t z0 theta minus z1 plus z1 minus x1, z1 minus z1. All right. So this is small, and this should be, it should be possible to make it small because z0 and right, z and z0 are nearby, right? So with my Lifschitz non-singularity, it's not going to matter much at all. It will all come out to be nice. I got to worry about this term though. And then this is nothing. Okay. So first, oh, I wanted that one. Okay, I'll write it again. So if you consider the first term, so we can call these as I1 plus I2 plus I3. So take I1, and that's going to be less than or equal to what? It's easier to one second. I1 means the first term without the modular sign, okay? So, so I have like this. So I1 would be, what is it equal to? E to the TA, Z0 minus Z0 plus integral 0 to t, e to the t minus s a f, right? F of x of t, x of s. What did I put there? Z0 theta minus f of x of s, Z0 theta. Take absolute value and take the bounds, and you're going to get what? You're going to get a Grunwald lemma, right? And that's going to make it all less than or equal to epsilon, because less than epsilon, because so is Z0 minus Z0. Therefore, Grunwald implies that absolute I1 is less than or equal to some constant times Z0 minus Z0. So less than Ct epsilon. And then take I2. For I2, what is I2? X of t Z0 theta minus Z1, right? The Z1 can be thought of as the process alpha that we wrote initially was there a Z0, Z1 or something like that at time capital T? Right? That's how we chose our alpha, right? It was just linearly going from Z0 to, in time, from Z0 to Z1. So if you do that, now the dynamics of alpha was given there by equation 1. Therefore, take the subtraction of those two, and what do you get? So now I2, that also without the absolute value sign, and looking upon Z1 as the terminal value, right, at time capital T of the process alpha, and that's just integral 0 to T. Notice that both of them start at the same Z sub 0. Therefore, there is no initial term, and then it is just T minus S A capital F of X of T0 theta, minus F of alpha Z0 Z1 of S. That's one term, plus integral 0 to T, another term, e to the T minus S in sigma theta of S minus beta Z0 Z1 of S. Okay, it's all quite boring. Therefore, put absolute value and then take the difference, right? And then this is just a constant, and then there is a Lifschitz constant that comes in. So you get exactly what you started with an I2, right? Namely x minus alpha, right? X minus alpha. So that's a nice thing for Grunwald type argument. So the first term doesn't pose any problems for us. Actually, it's a nice term. I don't know where. Okay. And then the second term, we have chosen sigma theta to be near beta, right? Therefore, that's going to be a small term. So Grunwald once again would mean implies that absolute I2 can also be made less than or equal to some other C prime, let's say, or C2. I call that as C1, right? Okay. Or C bar T epsilon. By the choice of our theta, we can make it small. Okay, so putting them all together, there were three terms, put them all together and it all becomes less than epsilon. So what does that mean? Thus, x of t, z0, no, x0, or z0 rather, theta, minus z1, that's where it ended, right? There was one term and then, so it all comes out to be 3 CT, some CT star, let's say, times epsilon. And that's what we wanted. That's called approximate controllability. So it comes out, so that was needed for proving irreducibility. And I told you, right, yesterday I warned you that it's from Grunwald, and that's what happens. Okay, any other questions? There's the all right, then I'll just stop here. We just have another 4 minutes, 5 minutes. Thank you. Yeah.
The impression you gave
Yeah.
is the loop theorem, right?
Correct.
Reducibility and
That's right. Strong feller would imply
yes, but then
invariant measure.
you also showed that if you have an invariant measure,
Right.
and you have something
Stochastic
like
and stability. Yeah.
But then that's another
Approach. Yeah. Yeah. You don't need necessarily to go through, right? The in existence of an invariant measure, strong feller and irreducibility to conclude that something is ergodic. right? You can there are also other ways to do it. These are only a set of sufficient conditions, right? So this sufficient conditions are not necessarily to be met to get the conclusion. So you can also get some kinds of stability, like what we proved, and then show that there exists an invariant measure, and that would be enough, right? And uniqueness of the invariant measure. Then that would imply that the measure is that the invariant measure is ergodic. That's another way. Third way is to talk about coupling, right? Cookson and Shirikian, actually their paper is simpler to read with kick forces. That means at the fixed times, there are some forces that are coming in the dynamical system. In our case, the Navier-Stokes system. The kicks are of finite magnitude, meaning bounded magnitude. So at those places, the process jumps. Right? And then from there onwards, it evolves like the Navier-Stokes equation. So this is the only stochasticity that's affecting the system, let's say. Then one can actually use certain Markov chain methods to prove the existence of an ergodic measure. Now you may ask, why ergodicity? Invariant measures, yesterday you saw a use for it, right? Namely in terms of reference measure, right? And then it also was given a certain form, right? Namely the Gibbs measures, right? Which are well studied. And also if you have a reference measure on a Banach space or Hilbert space, right? You can then form Sobolev spaces with respect to those, right? And then there is a infinite dimensional Sobolev space theory. All right. So W2, you can put W2 mu. Where to put mu? H2, let's say. But then with respect to the measure mu, H2 means W2 too, right? Things like this. So that opens up an area in analysis, for instance. Yeah. Right. That's right. It can even be a Gaussian measure. Usually they took Gaussian measure, but then Gaussian measure may not have any relevance to a dynamical system. Therefore, you can go to an appropriate measure as discussed yesterday.
So, for example, if I am studying PDEs in this space or existence of solutions in this space,
Mm-hmm.
since mu is invariant measure, it tells me something about the invariant measures of my solution.
That's right. Yeah, you can look at the. You are opening up certain new spaces, so to say, right? And actually, one studies logarithmic Sobolev inequalities on these spaces, right? Or hypercontractivity and spectral gaps. Oh, you do Malyavan calculus. You shouldn't say that. Yeah. Okay. So these are concepts that are right away introduced in Malyavan calculus, right? Hypercontractivity and spectral gap, of course, was a problem that Leonard Gross and others have been working on for several years. Yeah.
The role of sigma may probably merits discussion, because you see that as far as control theory is concerned,
Yeah.
sigma of low dimension range is the most interesting one, because you don't want to apply control everywhere.
Frequency, you mean low frequency. Yeah.
Physically localized, right?
Right.
And so there is this connection, right? So the best results, I think people appear to focus on
Or degeneracies.
when sigma is so the best controllability you have, you need to then bring in either this infinite dimensional counterpart of this Lie rank condition or Kalman estimates or things like that. On the controllability side. Likewise, also when you put a noise, it may be it's probably of interest. See that is noise is mostly focused on some harmonics.
Correct.
Or
Correct.
localized physical.
Okay. Then it comes in. Yeah, that's a good point.
That's the Mattingly paper.
Right.
At
Right.
on 4
A
dimensional.
and yeah.
You said that just put the noise in 4 harmonics.
No modes.
So then I don't know whether there's a proof to the corresponding controllability that was sort of claimed, and maybe Marco can clarify. Right? You just that discussion was there in your paper and also in Mattingly's paper. That okay, you have because they appear to rely on a controllability theorem, right? This sigma you have is a dense range, but I just give you 4 modes.
Right. That's right.
Then controllability is, there is Bakchil or something. The gentleman who wrote common rank type, Lie algebra condition for infinite dimensional problem.
Bakdan?
No,
Not Bakdan.
Actually, it's also
I see.
referred to in your paper. So the controllability appears to be
Right.
just to clarify.
Yeah, but one thing is it's not really local in space though. It is local in
Just give you 4 harmonics.
4 harmonics. Yeah.
I won't talk about that,
Yeah.
but I wrote something in the notes.
Uh-huh.
All right.
Yeah,
Thanks.
Yeah. So this is how I am formulating.
Right.
So either the noise or the control, let's say we give just 4 modes,
Correct.
right? 4 Fourier modes. What is the story on controllability, approximate controllability? What is the story on unique invariant measure? So this is because we had to get to the current state of the art and understand.
Correct. Yeah. That's right.
Yeah. I mean, I have some references for the controllability for Navier-Stokes. The right people to look at are those 2 Russian guys.
That's the name I'm looking for. Is it
Agashev and
Agashev.
Sarishev.
Yeah.
Agashev is in
Right.
Yeah. So Agashev takes finite dimensional controllability in the sense of Hector Sussman and the Lie algebra being full, and he generalized that to infinite dimension. And
I see.
So that's
Right.
you want to check whether that result holds for 4 modes.
Right.
That is what
Right.
I'd like to know.
That's
Because
right.
I couldn't tell that from Mattingly paper.
Okay, I think that Sarishev and Agashev result does not work for the 4 modes.
Uh-huh.
Their condition
Yeah.
is slightly stronger than the one that
Mattingly and
Martin and
Yeah.
John used in their
I know Mattingly's work and yeah, but
so since
it's there is a
controllability itself is a big industry,
Right.
in the control theory, and maybe the people who worked on that area
Right.
can also look at that and see whether that is so that those 2 ends meet.
Right. See, my interests are in one is ergodic control for Navier-Stokes equations, which others talked about, right? Who talked about it? Some of the control theorists, Professor Ghosh, and somebody else also talked about ergodic control. And the second is large deviations for invariant measures. Okay, so that's why I'm not bothered about small noise. Okay, small noise asymptotics. Yeah. So those are 2 problems. All right. So anyway, thank you.
So Professor Sundar is actually leaving tomorrow
Tomorrow evening. Yeah.
So from my
నేను పైకి సార్ తను పైకి
So when you said that you